Since the dawn of civilization, architecture has not only reflected the human soul but actively shaped and expressed it. Ancient temples, cathedrals, and palaces were not merely shelters but vessels of experience, designed to inspire and connect us to something larger than ourselves. The Renaissance saw architecture as a canvas for individual expression, with each building a bespoke creation. The Industrial Revolution ushered in an age of mass production, replacing bespoke designs with standardized blueprints and prioritizing efficiency over individual experience. Modernism further solidified this trend, emphasizing function and rationality, leading to uniform buildings, stripped of ornament and designed for an abstract standard individual. Current practices in residential architecture often rely on broad assumptions about user needs. Designing for the lived human experience necessitates a continuous feedback loop between the creator, the built environment, and its users. In the age of wearable technology, our bodies are becoming extensions of the digital world. Devices such as smartphones, smartwatches, and extended reality headsets continuously collect data on our movements, interactions, and physiological responses. This vast amount of data provides unmatched insights into our daily lives, habits, and preferences. However, this wealth of information has primarily been utilized for commercial purposes, such as predicting consumer behavior and influencing purchasing decisions. Yet this very same data holds the potential to be harnessed for a greater good, to enhance our lives and the environments we inhabit. While brain-computer interfaces, or BCIs, were initially developed to empower individuals with disabilities, their potential applications extend far beyond healthcare. Electroencephalography, or EEG, is a powerful tool that records electrical activity in the brain through electrodes placed on the scalp, beneath the skull, or directly on the cortex itself. These recordings capture the synchronous activity of neurons, providing valuable insights into brain function. EEG-based BCIs use this technology to translate neural signals into actionable commands, opening up a new frontier in human-building interaction. In my research, I used the Muse 2 headband, a commercially available wireless EEG device, to investigate the potential of this technology in architectural design. To bridge the gap between standardized design and individual needs in architecture, I propose empathic morphologies, a framework for creating spaces that respond and adapt to occupants' emotional and cognitive states through neurophysiological monitoring. As proof of concept, I developed two BCI systems. Fenestra, a passive BCI artwork that translates neural data into dynamic visuals, quantifying emotional responses to visuospatial stimuli. And Mentis, an active BCI-enabled VR experience allowing users to embody multiple characters with diverse perspectives, promoting empathy and informing inclusive design decisions. Fenestra is a passive BCI artwork designed to reveal the subconscious emotional and cognitive responses to visual stimuli. It captures neural activity using the Muse headband, translating this data into a dynamic visual language. For Fenestra, neural responses were recorded in CSV files as tabular data for post-hoc analysis. In Mentis, the Open Sound Control Protocol and a WebSocket connection enabled real-time interaction with the immersive environment through live streaming of EEG data from the Muse headband. To create an intuitive visual translation of this raw EEG data, a custom touch designer script was developed. This script established a baseline neural activity for each participant while they viewed a neutral gray screen. It then quantified fluctuations in alpha, beta, and gamma brainwave bands in response to specific visual stimuli. These brainwave fluctuations were then mapped to distinct visual cues. For example, decreased alpha waves, indicating reduced relaxation, trigger shrinking shapes, while increased alpha waves, signifying a calming effect, lead to expanding forms. Elevated beta waves, associated with heightened alertness, manifest as sharp, angular geometries, while reduced beta waves result in softer, more organic forms. Amplified gamma waves, reflecting intense focus, are visualized as intricate, well-defined shapes, whereas attenuations in gamma lead to diffuse cloud-like visuals. Fenestra employs two primary visualizations to translate complex neural data into meaningful representations. The first visualization establishes a baseline representing the observer's normal brain state across alpha, beta, and gamma frequency bands. The second visualization dynamically changes in response to stimuli, reflecting the observer's subconscious emotional state. To refine the translation of neural signals into a visual language, a user testing phase was implemented. A key component of this phase was the development of an emotional valenced video, specifically designed to elicit 5 core emotions: happiness, fear, sadness, disgust, and anger. The video incorporated neutral gray screens at the beginning, end, and between emotional segments to establish baseline markers and allow for clear observation of deviations in brain activity specific to each emotional stimulus. A series of workshops were conducted to validate Fenestra's ability to capture and translate emotional responses accurately. Participants were exposed to the emotional valenced video, enabling the observation and analysis of the relationship between specific emotional stimuli and corresponding brainwave patterns. This process aimed to create a comprehensive visual map of emotional impact directly linked to the dynamic output of Fenestra's interface. The culmination of the user testing workshops was the creation of a 6x6 emotion matrix, a visual representation of the neurophysiological responses of 6 participants across the 6 distinct segments of the emotional valenced video. Each column represents an individual participant, while each row corresponds to a specific emotional segment: baseline, happiness, sadness, fear, disgust, and anger. This visualization provides a comprehensive overview of the collective emotional response to the video and highlights the individuality of each participant's experience. Mentis is an immersive virtual reality game that utilizes EEG technology to explore how our perception and interaction with architectural spaces evolve throughout our lives. Using the Muse headband, Mentis translates players' brainwave patterns into in-game actions. Concentrated states enable interactions with the environment, while relaxed states trigger perspective shifts, allowing players to embody different characters inhabiting the same apartment across 3 distinct life stages. Mentis allows players to experience the same space through the eyes of a child, a young adult, and an elderly person, gaining a first-hand understanding of how our needs, abilities, and perspectives change over time. Beyond its narrative focus, Mentis also serves as a virtual testbed for exploring the future of residential design. The third and final level of Mentis envisions a world where brain-computer interfaces have become commonplace, seamlessly integrating with our living spaces to enhance comfort, productivity, and well-being. This speculative future involves subscription-based services for on-demand 3D printed furniture. Apartments feature built-in 3D printing robots that can print and unprint pieces of furniture using photosensitive composites and programmable matter, adapting in real time to user needs. Programmable matter can change its physical properties, such as shape, density, conductivity, or optical properties, based on user input or autonomous sensing, linking the concept to a material capable of performing information processing. When not needed anymore, a specific frequency of light dissolves the material collected by a cleaning robot for recycling. The level design of Mentis is central to conveying themes of change, adaptation, and the interplay between human experience and the built environment. From the warm, earthy tones of the 70s to the hyper-adaptive spaces of the future, the apartment chronicles the evolution of architectural design philosophies. Mentis offers players the opportunity to embody 3 distinct characters within the same level: the main character, a secondary human inhabitant, and a non-human inhabitant. Each character brings a unique perspective, shaped by their age, abilities, and relationship to the space. This multiplicity of perspectives highlights the diverse ways in which the built environment is experienced, based on age, physical capabilities, and social roles. It challenges our assumptions and underscores the importance of inclusive design. Mentis employs unique game mechanics that leverage both the VR headset's positional tracking and the player's real-time EEG data. Gaze interaction and sustained attention enable in-game actions, while relaxation facilitates perspective shifts. This creates an intuitive and immersive experience, allowing players to navigate the virtual space and viscerally understand different perspectives. To assess the effectiveness of Mentis in cultivating embodied empathy, I collaborated with researcher Isabelle Chauval from the Department of Brain Sciences at UCL. This collaboration allowed me to adapt her spatial evaluation framework, the Neurodesign Index or NDIX, for testing within a virtual environment. In Phase 1, participants were randomly assigned child, grandmother, or dog personas, completing tasks in a virtual apartment to highlight each perspective's unique challenges. For example, the child struggled to reach high shelves. Black and white visuals represent reduced visual acuity associated with young age, while the grandmother faced simulated locomotion and visual impairment. The dog, with its lower vantage point, relied on smell to find hidden objects. In Phase 2, participants repeated tasks using a less immersive BCI-enabled interface. Performance metrics, completion time, errors, workload scores, usability ratings, and subjective BCI feedback were gathered. User testing offered valuable insights into the potential of BCIs and VR to enhance spatial awareness and promote empathy. The VR experience effectively enabled participants to embody perspectives different from their own, while the BCI interface, despite requiring more cognitive effort, often led to a more engaging experience. Interviews were summarized and word clouds were generated for each persona. The NDIX analysis revealed significant variability in spatial experiences, underscoring the need for tailored design solutions. However, the lack of concern about data privacy raises important ethical questions that must be addressed. This research illustrates the potential of brain-computer interfaces and immersive experiences to reshape our relationship with the spaces we navigate and occupy. The future of architecture may lie at the intersection of mind and matter, and BCIs offer a glimpse of a world where our thoughts directly shape our surroundings, blurring the line between self and environment.